All right, let's dive into a real classic from Irodov's legendary problem book, number 1.72. Now, this one is famous for tripping people up, but we're going to break it down together step by step. You know, if you've ever looked at a diagram like this and just felt your brain freeze up a little, trust me, you are not alone. But stick with me. By the end of this, you're going to have a super clear, repeatable method to solve not just this problem, but a whole class of problems just like it. So, first things first, with any physics problem, you don't just jump in. The very first step is always to stop, take a breath, and break the problem down. Let's make sure we understand exactly what it's asking for. Okay, so the main goal is to find the acceleration of that hanging block, which we're calling body 2. But here's the really important part. The problem asks us to investigate the possible cases for its motion. See, this is where we go from just plugging numbers into a formula to actually understanding the physics at play. Now, before we even dream of talking about forces, F equals ma and all that, we have to tackle the geometry of the system. How does the movement of one block affect the other? Honestly, this is the number one place where people make a mistake on this problem, so let's nail it right now. Let's think about that thread connecting everything. It's a single, continuous piece of string. It's not going to stretch, it's not going to break. So its total length is constant. That simple fact is the key. So how can we use it? Okay, check this out, because this is the core trick of the entire problem. Imagine block 1 gets pulled, say, 1 meter up the incline. For that to happen, we need to find 1 meter of extra thread, right? Well, that slack has to come from the part of the thread holding block 2. But look closely. There are 2 strands holding that pulley. So to provide that 1 full meter of slack, each of those 2 strands only needs to shorten by half a meter. And that means block 2 only moves down half a meter. And that leads us to this. This is the golden rule for this setup. We call it a kinematic constraint. It means the acceleration of block 1 is always double the acceleration of block 2. This one little equation is the key that's going to unlock the rest of the problem. So tuck that away. We're definitely going to need it in a minute. All right, let's keep building. We know how the blocks have to move together. Now let's figure out why they move at all. And of course, in physics, that means it's time to talk about forces. We got to break it down one body at a time. And notice this super important detail, another classic trip-up spot. The tension pulling on block 1 is T, but the tension supporting block 2 is 2T. Why? Well, it's the same rope, so the tension T is the same everywhere in the rope. But block 2 is being held up by 2 strands of that rope, so it feels that tension twice. Okay, for our block on the incline, the first thing we do is break its weight down into components. The part of gravity pushing into the incline is canceled out by the normal force, so no movement there. The real action, the tug of war, is happening along the incline. We've got the rope's tension, T, trying to pull it up, and a component of gravity, m1g sine alpha, trying to pull it down. And the hanging block, way simpler. It's just a straight-up, one-dimensional fight. We've got gravity, m2g, pulling straight down, and that upward tension from the 2 rope strands, 2t, pulling straight up. That's it. Okay, look at that. We have all the pieces of our puzzle laid out on the table. We've got our kinematic constraint relating the accelerations, and we've got all the forces for each block. It's time to put it all together with Newton's second law, good old F equals ma, and solve this thing. So for body 1, let's apply F equals ma along the incline. We have to pick a positive direction, so let's just say up the incline is positive. That means our net force is the upward tension T minus that downward gravity component m1g sine alpha. And all of that has to equal mass 1 times its acceleration, w1. Now for body 2. Let's do the same thing, but in the vertical direction. And just to make our lives easier, let's call the downward direction positive, since we kind of expect it to fall. So the net force is the downward force of gravity, m2g, minus the upward tension, 2t. And that equals mass 2 times its acceleration, y2. So here's our plan of attack for the algebra. First, we're going to use our golden rule, w1 equals 2w2, to get everything in terms of the acceleration we're actually looking for, w2. Now we've got 2 equations and 2 things we don't know, the tension T and the acceleration W2. That's no problem. We can just do a little substitution to get rid of T, and that'll leave us with a final answer for W2. And bam! After the algebraic dust settles, this is what pops out. The acceleration of block 2 is g times this whole mess of masses in the angle. But hold on, we are not done. Getting a formula is one thing, but understanding what it's telling you, That's the real physics. You see, a formula is just a tool. A real physicist understands what that tool predicts. The problem specifically asked us to look into the possible cases, and this is where all the deep physical insight is hiding. This is the fun part. Just take a close look at our formula. Specifically, look at the numerator, the top part of that fraction, m2 minus 2m1 sine alpha. Now, the denominator is always going to be positive, right? Masses are positive. So everything, whether the block goes up, down, or stays still, is decided by the sign of that term right there. And this table just spells it all out beautifully. Remember, the problem told us that m2 is just some factor, eta, times m1. So what's really happening here is a competition. It's a battle between the mass ratio, eta, and this term 2 sine alpha, which represents the pull from block 1 on the incline. If eta is bigger, block 2 wins, and it accelerates down. If eta is smaller, block 1 wins, slides down the ramp, and yanks block 2 upwards. And if they're perfectly matched, the whole system just sits there in equilibrium. It's beautiful. So let's zoom out for a second. What's the big takeaway here? We didn't just solve one random tricky problem. We've actually developed a powerful step-by-step strategy. A toolkit, really, that you can use for pretty much any complex pulley system they throw at you. This 5-step process is your new blueprint. Step 1 is the geometry. Steps 2 and 3, that's the physics. Step 4 is the math. And step 5, that's where you show you really understand what's going on. If you follow this method, you can turn a problem that looks totally confusing into a series of simple, manageable chunks. That's the real key. I really hope this walkthrough has made things click for you. The next time you see some crazy-looking mechanics problem, you're not going to panic. You're going to have a plan. You'll know exactly where to begin. Thanks for joining me for this explainer.